Hello everybody. Let's look at an example of a monad because the abstract concept is possibly a little bit too abstract to really appreciate. So here's our favorite example of Hutton's razor, or a variant of it at least. So I've added in a set of variables into my expressions. So my expressions are either variables which are coming from this set, or numbers, or additional expressions, right? And what I want to do is I want to show that this actually gives rise to a monad on set. So for every set of variables, I get a new set of expressions over these variables. So what do we have to give? Well, we have to give a functor, and then a return and a join, and show that these laws hold. So first we have to define this functor. It's going to be whatever this is. And then we need these expressions. So let's start with the functor. So the functor here is given by an actional object. That's going to be our expr. So we're going to map x to expressions with variables from x. Then we need an f map. That's going to be our map expressions of this type. And then we need to show that this preserves identities and composition. So let's first define map expression. We do this in the usual way by looking at the expression. If it's a variable, then it comes from x, but we have a function x to y, so we can make a new variable in y, right? F of x. And otherwise, we are just going to recurse down. So for numbers, we keep them as they are, and if it's an addition, then we translate it to an addition and translate the sub-expressions like this. Right. Okay, and then to show that this preserves identities, we're going to use function extensionality. So now for every expression, we have to show that if we map it across like this, then we get the same thing out. So I'm going to do this in a lemma. This is A is a set. Okay, so we pattern match an x. If it's a variable, then we are applying the identity function to it. So REFL works as proof here. If it's a number, we leave it alone. And if it's a sum, then we know by the recursive calls that this will work in the summons. So we just use a Kong to deal with that, like that. Okay, so we preserve identities, and similarly we are going to preserve composition. Okay, so I'm going to use names for f and g, which are the things we are composing. See what we need to prove. This thing, okay. Don't know what x is. Okay, so we have to use the x from up here. Okay, and we do this by pattern matching an E again, right? So here, anything happens, we do the same thing on both sides. So that's REFL. Here we do nothing on both sides, and here we are just doing recursive calls. Okay, so we do have a functor, as expected, and now, as is usually the case when you want to get a monad, so you have a functor and you ask yourself, could this possibly be a monad? Then what's really important is that you have these return and join, right? So usually these laws will follow if you have these. So what does return say? It says that if we have an x, then we should get an expression with variables from x, but that's exactly what the variables are doing, right? So actually here we should be able to fill this in already. The underlying thing is just going to be the variable constructor, and the fact that it's natural, I'll get an x and a y and an f, and see that this is definitionally natural, so that's fine. But the real question is, what happens with the join? So here, what do we need? We need a way to take an expression where we have variables that are themselves expressions and turn that into an expression. So we need to define something like this. So what we should be able to do is, when we get down to a variable, we should just be able to forget that we're treating it as a variable and treat it as an expression. And for everything else we should just recurse. So let's see if we can do this. Okay, so here e is now an expression itself, so we can just return that. Forget that we treated it as a variable. For numbers we keep the numbers, and for everything else we just do a recursive call. Okay, I'm just busy, so I'm going to do this in the meantime. Okay, so that should be how we do this. Okay, and is this natural? Well, let's see. Okay, so we have to show an equation between functions. So let's use function extensionality. Okay, and now we have to show this. So again, let's do that in a lemma. Okay, that's okay. Okay, we'll do it by looking at E. In this case, everything is fine. This case is easy, and this case is just doing recursive calls. Okay, so it was natural. And now, what do these equations say? So this one, what do we have to prove? Well, whatever it is, it's really easy. So it's, if we first return and then immediately join, we get identity on both sides. Okay, what about this one? This one says, if you put a var constructor everywhere at the var constructors and then strip it away again, you should get the identity function, because join is stripping away one var constructor, right? Okay, so that seems like it should be true, right? You put one in and then you take it out. That should be the same as doing nothing. So let's see. I'll do this with function extensionality. And here we need to normalize that. We need to prove this. Okay. Okay, so this is the interesting case, and here we see that exactly the right thing happens. This is the easy case, and this is the case for doing recursive calls. So that was okay. What about this one? So here we're saying that if we first strip away one var constructor, so here x, let's do this with function extensionality first, so we'll see what x is. So x here is an expression where the variables are expressions where the variables are expressions. So we have 3 layers of expressions, right? So this one says that if we first strip away the outermost var constructor and then strip away one more, that should be the same thing as stripping away the innermost first and then stripping away one more. So that also seems doable, right? Let's prove that. Okay, so this is the only case that could go wrong, but it doesn't. Okay, so we have managed to prove that we have a monad on set, which is the functor that takes an x and gives us back expressions with variables in x. And by the way, if you think about what bind does for this monad, so we know that we can derive bind from join. What is the type of bind? And it says that if x and y are sets, and if we have a function x to x per of y, then we get x per of x to x per of y, and we get this by doing join after map expression of whatever we want. Bind of f. Okay. Let's join expression. Okay, let's look at this type. So this function here we can interpret as a substitution. It's saying for every variable we get an expression in y, and this says that we can then translate all the expressions in x into expressions over y. So if we have a substitution for the variables, then the bind gives us a way to apply this to a whole expression, right? So it's a very intuitive explanation for what the monad is doing in these cases. Just like the join here is forgetting one var constructor. If you look at the bind representation of the monad, it is doing substitution. So this is a general way to think about monads if you want. This is often a good example to think of what different things are doing.